Hello everyone. The topic today is routing. So we will dive into the internals of the internet and see the most important function perhaps. This is illustrating link state routing. So this is showing a database, in fact. This is illustrating what makes link state routing distinct from other routing methods, the fact that every router has an entire database describing the network. That's the principle of link state routing. Before that, let's discuss what is routing in general. Routing is a word that is overloaded with multiple meanings. Very often, routing means forwarding packets when you do it in a router, or more generally, by looking at IP headers. A switch is not routing packets because it looks only at MAC headers. A router routes packet. That's one use of this terminology that you will often find. But in our context here, routing means a routing protocol, which is the thing that routers do in order to know how to build their forwarding tables. We have seen, in fact, already one routing protocol for multicast. It's PIM sparse mode. We have seen that PIM sparse mode is a mechanism by which routers are able to know where to distribute packets. But PIM sparse mode assumes that there is a unicast routing method that is in place. So the forwarding tables for unicast are in place. This is what routing protocols do, and we will see how it works. There are essentially two widespread methods for routing in enterprise networks inside single domains: link state and distance vector. And there are a few other methods that we will discuss in a second. Link state is the perhaps most widespread method for routing inside a domain. What is a domain? A domain is a collection of routers that is under the administration of one company. EPFL is one domain, Switch is another domain, Swisscom is another domain. Google has many domains. So it is essentially a campus network or an enterprise network. Domains are then interconnecting using an inter-domain routing protocol, that's BGP, that we will discuss a bit later. How does link state work? Well, with link state, as I mentioned already, the main idea is very simple. It's like Google Maps. Every router inside a domain, or in fact, more precisely, an area, we will see that with OSPF, there are multiple subdomains inside a domain. So within one area, all routers have a complete map of the entire network. I have shown in the past some maps of EPFL networks, so you can think of it as the kind of things that routers have. How do they obtain this map? Not by having a network manager put the map into every router, because that's not what we want with routing protocols. We want that the routing protocols are autonomous. We want that the routers are able to find their routing table autonomously. That means in particular that if you add one router, everybody will recompute new routes, or if you delete one router because of a crash, for example, every router will also compute new routes. With link state routing, all routers learn the topology of the entire network by gossiping. What is gossiping? Gossiping means what happens when everybody repeats what they've heard to everyone without trying to process it. That's what makes the success of fake news, for example. So here, the news are the information that every router has locally. Every router knows. You have to configure it somehow. When you do that in the lab, every router has to know what is its own main IP address, what are the IP addresses of all the interfaces it has, and what are the subnets that corresponds to those interfaces. So it has, through this standard configuration, it has a local view of the topology. Now, what gossiping means is that every router will repeat that view to all the neighbors, and in this way, this information will propagate. We will see examples in a few minutes. Once routers have this, they have a complete view of the network, and then they use a shortest path computation, very much like Google Maps does it. When you want to go from A to B, you first collect a map. You try to find one or several equal cost shortest paths, and then this is how you will be able to forward packet. The only thing that routers keep out of the shortest path computation is the next hop, because that's the principle by default of IP forwarding. We will see later in the course distance vector, routing method that was very popular up to some years ago, still isn't popular in some Cisco routing protocol. It's called distance vector. Distance vector is very different. Assume you want to go to Bern, to the city of Bern. You're driving a car, and you're in the city of Lausanne, and you have no map, and no Google map, and no Apple map, or whatever. So how do you do? Will you be able to go to Bern eventually? Yes? By following the signs, exactly. If you're in a decent city, there will be signs, so they're probably green signs that tell you where to go to the highway, and when you are on the highway, you will probably see signs that will tell you where to go to Bern. Bern is a contrived example because it's probably written on all the signs, but that's the principle of distance vector routing. When you use distance vector routing, if you follow the signs, you follow a first sign that gives you Bern is turn to the right to go to Bern, and hopefully at the next intersection, there is another sign that tells you whether to go straight forward, which might be the default route, or turn left or right. In the context of networks, the intersections are the equivalent of routers. With distance vector routings, the routers don't have a global map. They don't know what the global network is. They only know for every destination which way to go and what is the distance to go there. So it's like if we would apply this to the road system, at every intersection, there would be the list of all the cities in the world, the distance to go there, and which way you have to turn. This is the principle of distance vector. It is considerably more sophisticated than link state routing intellectually, and we will talk about it towards the end of the course. Path vector is a variant of distance vector where instead of computing distances to a given destination, routers compute an entire path. A path being a collection of intermediate systems, which in this case are entire domains. This is used for routing between domains. We will have an entire module to talk about it, so I'll come back to that later. In some specific cases, there are other more exotic forms of routing. Sometimes they are used as a replacement for link state or distance vector routing. Sometimes they come as an addition. Here is one example, which is called source routing. Source routing is a method that is used, for example, in what is called ad hoc network. An ad hoc network is a network you deploy without any planned infrastructure. For example, after a catastrophe, an earthquake or a tsunami, rescue operations come, they deploy routers, they connect them with wireless links, and then all those systems have to find a path from A to B. So here I'm showing an example of a small deployment where I have a number of intermediate systems. Ad hoc networks can be simple PCs or even smartphones that are able to forward packets. And yeah, with one method that is used in such context consists in having the source, here A, that wants to send a packet to B. The source must find an explicit path through the network. In this case, an explicit path is R1, R2, R4, and then B. We'll see in a minute how a source can find that. Having found this explicit path, what a source does with this method of routing is write the entire path in the IP packet header. Of course, normally in the IP packet header, you only have a source and destination field. So a way to do that is to add an extension header. With IPv4 or IPv6, it is in principle possible. And then a little optimization. So normally if we add an extension header, would mean I send from A to B, and I have to put the path here. But in order to simplify the processing by routers, what is done is we substitute the destination address by the next hop along the path. And then the routing header has the rest of the sequence. So when A sends this packet, the destination address is R1. It's not the true destination address, but if there would be intermediate systems that are able to forward the packet, they will send it to R1. Now, R1 sees that there is a routing header, so it knows perhaps the packet is not really for me. I have to check what the routing header is. It will see R2. R1 will process the header, remove R1, replace it by R2, update the routing header, and the packet will go to R2, R4 will do the same. This is a very primitive form of routing that has the benefit that the intermediate systems have very little to do. They need to process the packet headers, but they don't need to know what they are doing. They don't need to know which directions packets are going. So there is no routing protocol between the intermediate systems. Of course, there's a price to pay. The source needs to know how to go from A to B, and this is typically done by flooding. So A will send an exploratory packet that is flooded, and this exploratory packet will collect all the paths. So A sends a packet, this packet both to R2 and R1. R1 will repeat it to R3, will not repeat it to R1, because when R1 receives it, it will mark that this packet is coming from A. But you will send it to R2, and R2 will receive it. It will see, I have one copy that comes from A, one copy that comes from R1, from A and R1, and it will, probably in some of the protocols, it will forward both, so that at the end, B will receive probably a large collection of packets, each of them having a path marked. Then B will typically make a decision, for example, take the one that comes first, and then has the path and sends the, following the reverse path, will send it to A, who will have this information. That's the kind of things that is done in ad hoc routing protocol. That was done also in the past in some bridging technologies, token ring bridges. And this is called strict source routing. Why strict? Because there's another form of source routing which is more important today and is deployed in private networks such as data centers, which is called loose source routing. Loose source routing, the difference is that in strict source routing, the packet header contains the entire path. And we don't need any routing protocol inside the network for this to work. Loose source routing is something different. It is giving via routers, via nodes. It is giving the instruction in order to go from A to B, you must go via those intermediate points. But it doesn't give how to go to those intermediate points. So it's similar to what you do when you go to the CFF website. You say, I want to go to Bern, but I would like to do a stop in Palaisieux. Then CFF will give you a train itinerary that stops in Palaisieux. That's exactly what loose source routing is. So here, for example, assume A wants to send a packet to B, but for some reason, A wants that this packet goes via R4, R2, and R5. It wants that it follows the red path. And it knows that in order to go to R4, it will automatically need to go via R1 and R3. So in this case, A doesn't bother putting the path R1, R3, because here we're assuming there is already another routing protocol that is in place. So A knows how to send a packet towards R4. So otherwise, the rest is similar. This source routing header the first element of the source routing header takes the role of the destination address. And here a benefit is that only R4, R2, and R5, the routers that are involved in this loose source routing decision, need to do something about the packet. Routers such as R1 and R3 don't do anything specific. They send the packet towards R4, so they do not have to process the packet header. Why would anybody like to do this? Well, there are reasons such as traffic engineering. For example, perhaps this path is better for some kind of traffic. Perhaps that's traffic that is consuming a lot of bandwidth, and the link between R4 and B is perhaps an exposed link that we would not like that this low priority traffic goes this way. And A might be, in fact, an edge router that is able to make such decisions. So that's a way to do traffic engineering by taking decisions only at the edge of the network instead of doing it everywhere in the network. But more importantly, very often this is done to separate the traffic of customers, to force customers to go through some paths, or even in specific case, Perhaps because we know that in R2 we will do deep packet inspection, for example. So if this flow is a flow that is a bit suspicious, we might force this flow to go to a router. Well, it will receive some specific processing. Those functions can even be extended in what is called segment routing. So if we do loose source routing today, we use what is called the segment routing header in IPv6. It works with IPv6. It doesn't work with IPv4. In theory, it works with IPv4, but in practice, all routers destroy any source routing header extension of IPv4, but not of IPv6. Because for IPv6, there is a provision for a signature. So there is an authentication of the routing headers that can be verified here. We can talk about that if there are questions. Segment routing does the same, except it allows more sophisticated things. So in the segment routing header, you can give an address. For example, if you give the address of R4, you can give to R4 not an IPv6 address, but an IPv6 prefix. Because in IPv6, as we know, we have lots of addresses. So IPv6 R4 may own a 64-bit prefix. So any source routing header that has this prefix will end up in R4. And then we can use the remaining 64 bits, for example, to give instructions to router R4. We have 64 bits to write an instruction. So the instruction might be, do deep packet inspection on this flow, or serve it as a low latency flow, or whatever you want to do. So this is opening the box of what is called active networking, where you can mark in the packet header things that are not just addresses or instructions for routes, but instructions for processing. So this is something fairly recent, not yet fully deployed in the internet, but it's deployed, as I said, in big data centers, for example, to have explicit routes for packets in order to satisfy a number of business constraints. Now let's dive into the topic of this and next week, which is link state routing, and in particular OSPF. There are essentially two link state routing protocols, OSPF and IS2IS. OSPF is, I believe, the most widespread. They are very similar, so we will not see both, we will see one of them. The terminology is a bit different from one to the other, so in the lab we will do OSPF, and in the course we will do OSPF. So as mentioned, every router has an interface the goal of a router of OSPF is to deploy, to make sure that every router is able to gather the total topology information for the entire network. In fact, not exactly the entire network, because OSPF has the concept of areas. So OSPF does link state routing inside one area. We will see a bit later what happens between areas. So link state routing is only valid inside one area. In order to know the total topology, every router needs to know its local information. This is called the interface database. And then it will collect the link state database using gossiping. It will also maintain information about which routers are its neighbors. This is useful in order to discover whether there is a failure somewhere, in particular, for other reasons, but also for this one. If a router A and a router B are neighbors, they should talk OSPF if they are configured to be in the same area. So they should talk OSPF, and by talking OSPF, they also monitor each other. So if one of the routers crashes, then all the neighbors will detect it, and they will flood new information to update the topology database. So this is the fundamental mechanism by which the topology will be adapted to the current state of the network. One way of doing that is called the Hello protocol, which is a very common protocol we find practically in many distributed systems, and in particular in routing protocols. A Hello protocol simply means that every so-and-so, for example, every second, a router sends a packet, says hello to the neighbors, and expects a response. And if after a number of instances no response has come back, you decide that this router is dead. This mechanism exists at the level of OSPF. It exists also at lower levels. For example, Cisco routers implement a protocol called BFD that does the same thing, but very frequently. They send a message every 10 milliseconds, so that if one router or one link between two systems is dead, within a few tens of milliseconds, this is detected. So let's see the details of how this works. So some terminology, the topology database is called the link state database. Link state is the information that every router sends about its local information. All this information put together gives the link state database. So the link state database is simply a list of records called link state advertisements that are sent and recorded. So a router sends LSAs about itself and records in its link state database all the LSAs it has received from indirectly or directly from all other routers. The link state advertisements contain a sequence number. The sequence number is useful to avoid loops when we flood. We will see in a second how this works. So let's illustrate on a very simple example the operation of OSPF. This is a toy network, not very realistic. In the lab, you will have more realistic ones. It has so far 1, 2, 3, 4, 5 routers. A bit later, we'll add a 6th router here. It has point-to-point links that are shown with these special lines, and it has Ethernets or local area networks that are shown by these different types of lines here. Initially, assume hypothetically, we start all the routers together, which in fact will never be the case, but assume this would happen. Then every router has its local information. If we zoom on B, we see that B knows it has an interface on some interface. It has a network with a network prefix N3, so that's the 128.178.156/24, for example. So it gives both the prefix and the length. It knows also the type of the network, in particular whether it's a shared medium like Ethernet or the standard local area network, or in contrast for the other network, whether it's point-to-point. We will see that there's a small distinction for OSPF in those two cases. Here also OSPF will try to optimize things by detecting whether some networks are stub or not. Stub means this is an interface on which we think there should not be another router. We don't expect to speak OSPF on this interface here. In contrast, on the two other interfaces, we expect to speak OSPF. We expect that there would be other routers. And so you see that there are local database, interface database, and every router has its own interface database. Of course, there is some overlap. For example, B and A are on the same link that has the same prefix N2, so they know through this way that they are, in fact, on the same network. Then, when B starts, it will flood its local information to all the neighbors. So, for example, it will send it to A, this information that is in its interface database. It will send it also to C. Now C will receive it from B, and flooding means both A and C will repeat it. So C will repeat it to A via N1. So A will receive this information first hand from B and second hand from C. But when it receives it from C, it will know who is the source, this is A, and there is a sequence number in every link state advertisement. So A will know this is this source, this number. I already have seen it. So when A will receive the advertisement secondhand from C, which probably would come after the number one here, it will know that's a duplicate of something I have already, so I can safely ignore it. I don't need to do anything in my link state database. And then C will forward to D, and D will forward to E. This is sent using UDP. So OSPF has to do all the things we do when we do a UDP program, like you're doing in the lab. It needs to wait for acknowledgement, send a timer, and for every link state advertisement that is sent or forwarded, it expects to receive an acknowledgement. After flooding, all 5 routers will have the same database, which contains all the information that has been sent by everyone. So it will be the same in all the routers. Here there's a little thing that is special to OSPF. The link state advertisement, this is what B had in its link state data, in its interface database, and we find it verbatim here the same. Now, OSPF treats what it calls shared medium networks, which are the local area networks, which are most of the time point-to-point, but very often shared medium. For example, if this is a switched Ethernet, there are 2 routers, but there could be more than 2. We'll see that the third one will come in a minute. What OSPF does in cases like this, it treats the shared medium network itself as a node in its graph. OSPF will need to do shortest path computation, so it treats those shared medium networks as nodes. In some sense, it assumes there is a bridge. It doesn't speak because a bridge doesn't know IP, but this is how it thinks about it. And then the OSPF protocol will elect among all the routers, here A and C, when they talk together at the beginning, they will both see, oh, we are on the same network N1. We have to elect one of us as what is called designated router, which is the one that will speak for the network. In this case, I'm assuming it is C, so it means that C will speak for N1. That means C will send an advertisement saying, I am also speaking for network N1, and network N1 is an Ethernet network, and it has a cost of, so all those networks are expected to have costs. Now the cost of a network is 0, we'll explain why in a second, and it gives all the lists of all the routers that are on this network. So in particular, this means that A will not speak for N1, but A will simply say, I am on N1, and the designated router for N1 is C. So for all details about N1, you need to go to C. This is how things are done with OSPF. We'll see that this comes from the need to do shortest path routing on a graph, and a graph cannot have nodes that are multiple nodes. Here. Assume now that F, that is also in this network, but boot a bit later, which is a typical case. Even if you press the boot button on all your 6 routers very close together, probably the routers are not all in the same room, so you need to take your bicycle and go very quickly from one to the next. So here F is started a bit later. Then we will see what OSPF does. Now, because before F started, OSPF had stabilized, and there was a topology database in E and C that has stabilized. That means it knows it has converged here. Now, when F starts, it will discover that on this interface there is C and A, and on that interface there is E here. Assume it discovers first C, then because F is just starting, the first thing it will do is it will copy all the information that C already has. This is called synchronization. So the reason is that OSPF tries to not flood the information unnecessarily. So if F did not do that, it would need to ask all the routers to flood the thing. But it's more efficient to ask a neighbor to do that. So it will copy all the database that we've seen in the previous slide. And once this is done, it will consider now my adjacency to C is achieved here. It will also see that there is A, but now it knows that the designated router is C. By the way, by triggering that, that might change who the designated router is, but let's assume it keeps C, so it doesn't need to bother A about what is happening. Then a bit later, when this is done, F will start speaking to E, and we'll do the same thing. But now F already has a topology database, so it will simply ask E to give the delta, the difference between the topology database, which in principle should be empty, because E was synchronized with C, so F will very quickly say, oh, we are fine, we both have the same topology database. And when this is achieved, then F will participate in the flooding mechanism. So what we see here is that OSPF does flooding, but in order to avoid inefficiencies and very long convergent loops, it always requires that a new router synchronizes with all its neighbors, learns what has been already flooded before starting flooding things itself. So after flooding, this is what we will see in all the topology databases. Of course, what F will also do, it will flood its own interface database, which will change the topology database of C, but it will do that only after synchronization. So C will flood it to B, etc. So at the end, or after some time, all routers now will have this new information coming from F, and the network advertisement from C is the designated router for N1, will have new information saying F is present. On N7, there will also be, assuming this is a shared medium LAN, we need to know, the two routers E and F will need to decide who is the designated router. Here, I'm assuming this is E, and we will have this information in the topology database. A graphical representation is given here. Yes, question?
In the previous slide, if F moves later, can it be the designated router? Because first it was C, right?
Yes.
Then F would be the designated router.
That's a good question. I assume yes, but we would need to verify. I assume yes. Yeah. Although if I would design the protocol, if I say I already have a designated router, why would I change it when somebody joins? So I would do a lazy thing, but I'm not 100% sure this is what OSPF does. So the topology database can be mapped to a graphical representation. This is not done. We don't draw pictures inside a router. But if we do it, this is what we would see for this network. We see we have a network which is unidirectional with link costs that correspond to the configured values. Similar to what we saw when we discussed the spanning tree of bridges, you typically give small cost to links that you want to be used, so the high bitrate links, and large cost to the links that are either low bitrate, they are there for backup purposes, or for local service only. So this is what is given here. Perhaps those point-to-point links are of a cost of 100, and the shared media link that are on a fast Ethernet have a cost of 10. Now, because the only way we can compute shortest path is to assume that we have only point-to-point relations between nodes on the network, we add a virtual node for the network in case a network is interconnecting several routers, which is the case here of network N1. We have a switched LAN, for example, on which there are 3 routers. In this case, we add this virtual node, and we've seen that the designated router speaks for it. And in principle, what we do, we add a cost of the true cost to go to N1 and a cost of 0 to come back from N1. Although this can be changed if you insist, but that's the default behavior. So this is the graph that is acquired by all the routers. But of course, the goal is not to have a graph. The goal is to do routing, to know which direction to go. This we will see in a second. So OSPF packets, I said UDP, I said something wrong. I said OSPF packets are sent directly over IP with an OSPF special protocol number for OSPF. And the transmission is in principle as if it would be with UDP. Reliability has to be managed by OSPF itself. In the graph, I showed routers as A, B, C. So routers have an identifier, which is a 32-bit number, even if we use IPv6. So it's a number that is used to describe the graph and do the shortest path computations. Now, having acquired a topology database, the main interest of all this story is to be able to compute paths toward destinations. So by default, OSPF, like distance vector routing protocols, compute shortest paths from everywhere to everywhere. It's performed at every router based on the link state database. So every router computes the shortest path from self to everywhere. All routers have the same topology database, but since routers compute the path from self, they compute different paths. on the same topology database, because the shortest path from me to you is not the same shortest path as from him to you. The best known algorithm to compute shortest paths is Dijkstra's algorithm, best in terms of complexity. So this is the one that is used here. It's the best when we do centralized operation. By centralized operation here, I don't mean that there is a central network controller that's computing all the paths. We don't want that when we do routing protocol. We want all routers to do things autonomously, because if we had a central controller, the problem is how do we go to the central controller? We will see that we have SDN for things like this, but with routing protocol, we need that the things are done locally. So centralized operation here simply means that every router computes the path to everywhere based on its view of the complete topology database. This is in opposition to what distance vector does, which we will see in a few weeks, where everybody does local computations only, and the computations can be totally distributed. Here it is, what is distributed is the flooding. The acquisition of the database is distributed in the sense that everybody participates in it, but at the end of the flooding, everybody has the same database. So it's not a true distributed protocol where everybody does a part of the computation. Here is one pseudocode for Dijkstra's shortest path algorithm. There are many versions depending on how you want to optimize things, but this is probably the closest to what is done in the OSPF code. Not exactly, I will explain, well, it's explained a bit later in the slides, but that's the version we will see because that's the one that's easier to understand. More precisely, what we see is that the algorithm, it has a number of nodes that are here labeled 0 to n, and 0 is this node. So we want to compute from this node what is the path, what is the shortest path to all possible nodes. For that, it keeps two state information. One, the m, which is the distance that is known at this stage of the algorithm. So it's an estimated distance from self to this node. At the end of the algorithm, it's the true distance. If the algorithm works well, which is the case, Dijkstra has been proven to compute the shortest distance. So it will, at the end of the algorithm, be the distance, but in the intermediate steps, it might not be. And the second intermediate Dijkstra structure is a set of nodes, which I call V here, which are all the nodes that are added one by one. We will see that the algorithm adds the nodes one by one. And at the end, V contains all the nodes. And Dijkstra has the property that when a node is added into V, the value of the estimated distance is the good one, is the correct one. And the algorithm is very simple. There are small details because of equal cost multipaths. But if we ignore this, it's very simple. It does exactly the sentence that is done here. It iteratively adds one node by adding the node that has the shortest distance estimated at this point. Right. That's what it does. It starts by originally giving to itself a distance of 0 and a distance of infinity to all other nodes. So let's take a simplified version of the network we had before. So this is showing the evolution of the algorithm. Now we do the algorithm at A. Right? Remember in Dijkstra, in this network where there are 6 routers, there will be 6 instances of Dijkstra, 1 per router. And the 6 instances will compute different shortest path because they are rooted at different nodes. Here we are rooted at A. The set V is the nodes that are in pink. Now it's empty initially. And the value of the estimated distance is the box here. The yellowish boxes here that are given here. Those are the estimated distance from node A to this node. So initially, when we start, the distance from node A to node A is 0, and from all to all other nodes is infinity. Right. Now, at step 1, what does the algorithm do? Well, it computes. It does It will add the node that is given all the state here, the one that is the closest. Now there's only self, A, all the other are distant infinity. So it will add A to the tree. We could also take that as an initialization if you want. And then when it does that, it updates the estimates of the distance. Because now it sees A is on the tree, I will look at all the neighbors of A, all the systems that are directly connected to A. Here there are 3, B, C, and F. I know the distance to A is 0, so my estimate of the distance to B will be 0 plus the cost of the link that goes from A to B, 100. So the estimate of the distance to B is 100. My estimate of the distance to C is also 10, and my estimate of the distance to F is 10 here. My estimate of the distance to D and E are still infinite here. So we modify the estimates of all the nodes that are directly connected to the nodes that we have added here. And we also do more. We remember in the form of the arrow that is given here, what was the best way to go from A to C here. So seen from the viewpoint of C. Now there's only one that was found, so the only link that we've added is those links marked in red here. That's the first step. Now, next iteration, what will the algorithm do? It will add to the tree the nodes that are the closest. So it's C or F. Now, it needs to add only one. So it will pick one of the two. Perhaps it goes by alphabetic order in this case, or by the ID of the algorithm here. Assume it will add C. So we add C to the node. So we have now added C. By adding C, I also update the distances by looking at all the neighbors of C. C has neighbor A, which is already taken into account. We can ignore it. So we look at all the neighbors that are not yet on the tree. So we have B, D, and F. The distance, if I add B, the distance I have is 10, the distance to C, plus 100, that's 110. This is less good than the distance we had before. So I ignore it. I consider that going from C to B is not a useful thing to do. So I don't change anything at B. From C to D, the distance was infinite, and now I know a distance of 10 plus 20, which is 30. So 10 is the distance M of C, plus 20, that gives 30. So for D, we know something better. And for F, we can also do the update. We find 10 plus 10, which is 20, but I had something better before, which was 10, so there is no update. So I've updated the estimates of the distances. I also have added new directions on where to go there. If we had found that going from C to B was less expensive than going directly from A to B, for example, if the distance here had been 10 instead of 100, then we would have changed the red arrow. Now it would go from C to B. This is what we would have done. Then the next step will be here to add a node that is the closest in the estimated distance. It's F, that is 10, so we will add 10, and we will do the update, and the update, F has neighbors that are outside V, the only neighbor is E, so we look at the new value we obtained for E, which is 20, and the direction to go to E is this one. This is what happens at the end of step 3. What will happen at step 4? Imagine for a second that you are a computer implementing Dijkstra. And the correct answer is C, as practically everyone has found. But there is something interesting that happens here. We add node E, which is answer C, because it was the closest. But when we add node E, I update the distance from E to its neighbors. Now, the only new neighbor that... The only neighbor of interest is D, so I found a distance to D, which was 20 plus 10 is 30, which is not better than before, but is not worse either. So it means we have found a second path that has the same value as before. What Dijkstra does is records all those things. So if there are multiple paths that have the same cost, it will remember them and, if possible, use them. So in that case, what happens is the value, the estimated distance to D is not modified, but the data structure, the predecessor, which indicates how to go towards D, will be updated by saying now, I have two ways to go to D. Is the previous one we had, this red arrow that points back to C, but a new one that points back to E. So the predecessors of D are now C or E. Voila, we will continue the suspense of how Dijkstra will manage this network after the break.